So here's another example about the work by a variable force. In this example specifically, we will calculate the work done by an elastic force. The elastic force of a spring is determined by Hooke's law, which tells us that the force of the spring is going to be equal to minus kx. Here k is the spring constant and x is the displacement of the spring from its equilibrium position. If the graph on the screen here shows the elastic force for a certain spring and how it depends on the position of the stretching, determine the work for the displacement from x 20 meters to x 60 meters. We're going to start with the fact that the work of a variable force in one dimension is going to be simply the area under the graph when we plot the force on the y-axis and the displacement x on the x-axis. So for the area, what we can do here is, just as before, we can highlight the area under the graph, which is actually a trapezoid, and we can break it into two, one rectangle and one triangle. Many students know the formula from geometry for the area of a trapezoid, and here it's perfectly acceptable just to go with that formula and calculate the area immediately. That will be the sum of the two parallel sides, in this case is the left and the right side of the trapezoid, multiplied by the height of the trapezoid, which will be the top side of the highlighted area, divided by 2. But I want to go and break this area and calculate the area in slightly different form. Again, if you remember the formula for the trapezoid, it's absolutely not necessary, but at the same time, my approach links to some concepts from physics, such as work and potential energy, and helps the understanding of what is going on in these problems. So what I'm going to do actually is, instead of breaking the trapezoid in a rectangle and triangle as we did before, I'm going to actually look at this big triangle that extends all the way to 0, and I'm going to calculate its area, and then I'm going to subtract the small triangle here that extends from 0 to 20. So let me mark that position x1, which is 20 meters, and the area for the small triangle that extends to that first position x1 will be a1. Then the big triangle that has for its base that extends all the way to x2, I will mark as a2. And now I can look at the areas of those triangles. Let's start with the big triangle a2. From geometry, I know the area of the triangle will be 1/2 the base times the height. We're working with right triangles, so it's going to be simply the product of the two sides here. So the area of the big triangle is going to be 1/2. The base is from 0 to 60, so the length here is 60 meters, and the height is minus 150. Note that I'm keeping the minus. So that gives me for the area under the area of the big triangle to be minus 4,500 joules. The area of the small triangle A1 is going to be 1/2 the base of it, which is from 0 to 20, so that gives me a length of 20 meters multiplied by the height, which according to the diagram is minus 50. So I'm going to put minus 50 here, and that gives me for the area of the small triangle to be minus 500 joules. What is left here is just to figure out now the work as the total area of the trapezoid, which will be the difference between the big triangle and the small triangle. Or numerically, it will be the area of the big triangle minus 4,500 joules minus, so remember there's two minuses here, which will flip to plus 500 joules for the area of the small triangle, which gives me for the work done by the elastic force to be minus 4,000 joules. Now let's redo the problem with symbols. I want to show you something. The problem is over and you know the answer, but here I want to show you how many problems sometimes ask you to work everything in symbols. So if we go back and mark x1 and x2, let's see what the work of the elastic force will be in terms of those symbols x1 and x2, and possibly k as the spring constant. So I will have to use Hooke's law, which is fx, is always equal to minus kx. So I'm going to go and mark the value for the function at x1 to be minus kx1 and the value at x2 to be minus kx2. With that, I can go back to my triangles and look at the big triangle, the area of the big triangle A2 is going to be equal to 1/2 the base, in this case stretching from 0 to x2, so the base will be x2 minus 0, or just x2, and the height will be minus kx2. So I see here that the area of the big triangle is going to be minus 1/2 kx2 squared. Similarly, for the area of the small triangle, I will have 1/2 x1 minus 0 times the height, which is minus kx1. And so here the area is going to be minus 1/2 kx1 squared. And so the work, which once again is going to be equal to the difference between the big triangle, the area of the big triangle minus the area of the small triangle, will be the area of the big triangle A2 is minus 1/2 kx2 squared minus the area of the small triangle, which is minus 1/2 kx1 squared. Again, we have minus minus, which flips into plus. So I see for the work of the elastic force of the spring, as an object moves from x1 to x2, that it is going to be equal to minus 1/2 kx2 squared plus 1/2 kx1 squared. Does that expression look familiar to you? We have seen similar function that goes by 1/2 kx squared in the past examples. That was when we calculated the potential energy associated with the elastic force of a spring. Back then in those examples, we used for the potential energy the formula 1/2 kx squared. So if we were solving this problem for the mechanical energy of the system and we had to look at the potential energy associated with the elastic force of a spring, I will have to write that the potential energy at location x2 is equal to 1/2 kx2 squared. And the potential energy at x1 is 1/2 kx1 squared. So I can see that the work actually is showing to be minus the potential energy at x2 plus the potential energy of x1, which is really the opposite of the change in the potential energy. So we're back to actually the definition of potential energy. Remember, the potential energy associated with the conservative force is always defined so that the change of that function will always be equal to minus the work of that conservative force. And one final note here for those who are familiar with calculus. I want to show you how easy this problem and how quick it can be done if we already know calculus. So for students who are familiar with calculus, you don't have to work with this formula for the work, but we can go back to the basic definition of work of a function in one dimension, which will be the integral of f dx, and here I have placed also the limits from x1 to x2. I'm going to use Hooke's law, and so f is going to be replaced by minus kx, and I'm going to calculate this integral, which is going to be minus 1/2 kx squared, with limits from x1 to x2. So what is left here is just to put those limits and evaluate the work. So the work comes out to be minus 1/2 kx2 squared minus minus, which flips to plus again, 1/2 kx1 squared. We are back to the opposite of the change in the potential energy.